Hello, everyone. My name is Jeff, and I will present our ICASSP paper on the interplay between sparsity, naturalness, intelligibility, and prosody and TTS. And this is mainly joint work with Erica from NII and Ying from MIT IBM AI Lab. From a recent survey on neural TTS, out of the a lot of the papers in the past 2 to 3 years, only very few of those are on efficiency and TTS. In particular, there's no paper that utilizes pruning techniques to achieve efficiency in TTS. One of the future research directions on neural TTS is efficiency. And in particular, the broader impact of our work is on reducing the cost of training and serving TTS models. We will look at parameter efficiency, and we will achieve this by pruning. We have 3 models: Transformer TTS, Cyclotron 2, and Parallel Waveguide. Transformer TTS and Cyclotron 2 shares the same high-level model architecture, that they have an encoder module, an autoregressive decoder, a prenet, and a postnet. So in our pruning algorithm, we're going to prune all 4 of these modules jointly. The parallel waveguide consists of a generator, which is a wavenet, and a discriminator. Because only generator is needed for test time, we only chose to prune the generator. The reason for choosing these 3 models is because there is public implementations and pre-trained models available. And we want to ensure that our insights are reproducible and useful. So this is the model setup. We have 3 models, and we take the pre-trained models on OJ speech as the initialization for our pruning algorithm. This is one of the 2 pruning algorithms that we use in our project. So the first pruning algorithm is IMP. IMP is very simple. It takes the pre-trained model, such as pre-trained Cyclotron 2 on LJ speech, apply unstructured magnitude pruning, which returns a sparse subnetwork. This sparse subnetwork then goes through another round of training, also on LJ speech. And this step is called subnetwork retraining or subnetwork fine-tuning. The output of IMP is a trained sparse subnetwork on LJ speech. The second algorithm is PARP, which is a simple modifications of IMP. The difference of the key modifications of PARP is that during subnetwork fine-tuning, the zero out weights from the initial UMP operation are allowed to grow back with gradient updates. And the final output of PARP is also a trained sparse subnetwork on LJ speech. This is a comparison between IMP and PARP, and we encourage you to read more about these 2 algorithms in the paper and in prior work. So we're going to use these 2 pruning algorithms to prune the 3 models we mentioned before. So there are 4 model combinations: prune Cyclotron 2 or prune Transformer TTS paired with an unpruned parallel waveguide, or an unpruned Cyclotron 2 or an unpruned Transformer TTS paired with an pruned parallel waveguide. So there are 4 combinations for our experiments. The prune models synthesis is then evaluated for naturalness, intelligibility, and prosody. Naturalness is quantified by a 5-point scale Mohs test. For intelligibility, we pass the synthetic speech to a Google ASR BI to get the synthetic word error rate. For prosody, we measure it by the mean and standard deviation fundamental frequency estimation, and also the average utterance duration. So now we're gonna go into the 3 scientific questions we explore in this study. The first question is, how does sparsity affect naturalness? And these are the most plots. The y-axis are the most score, and the x-axis are the sparsity values of the model. The top 2 plots are pruned transformer TTS and pruned tachytron 2 paired with an unpruned parallel wave GAN. The main observation is that there is no statistical difference up to 90% sparsity. We also observed that at 30% sparse tachytron 2 actually produce more natural synthesis over the original tachytron 2. This leads us to the first hypothesis that pruned model could train better. The bottom plots are the original transformer TTS and tachytron 2 paired with a pruned parallel wave GAN. There is no statistical difference up to 88% sparsities in terms of naturalness. So this leads us to the second hypothesis that neural TTS are overparameterized in terms of naturalness. The second question we look into is, how does sparsity affect intelligibility? The top plot here is plotting synthetic speech word error rate over sparsity values. So the first 2 observation is that for transformer TTS, the synthetic speech word error rate actually reduces prior to 90% sparsities over the unpruned transformer TTS. For tachytron 2, the synthetic speech word error rate doesn't decrease, but it maintains the same for up to 40% sparsity. For parallel wave GAN, there is no word error rate change at all for up to 88% sparsity. So based on these observations, we can conclude that neural TTS are overparameterized in terms of intelligibility. The third question we look into is, how does sparsity affect prosody? The top plot here is plotting utterance duration over sparsity values. And we see that for transformer TTS, there is minimal duration fluctuation. While for tachytron 2, there is a linear decrease over sparsities. And this implies that the synthetic speech actually speed up when we prune the model more. For parallel wave GAN, there is no duration change at all. In the second plot, this is plotting F0 mean over sparsity values. We see that the fundamental frequency mean jumps around for tachytron 2, while it's relatively stable for transformer TTS. And we attribute this to the instability of tachytron 2 pruning. While for pruning parallel wave GAN, there is no change in F0 mean at all. So based on these observations, the fourth hypothesis is that vocoder is not responsible for prosody generation. The last plot here is plotting F0 standard deviation over sparsity values. There is minimal F0 standard deviation variation comparing that to the ground truth 53 Hertz F0 standard deviation. This implies that there is minimal F0 oversmoothing, which is a key aspect in waveform modeling. And this gives us the final hypothesis that pruning does not hurt prosodic expressivity. With these experiments, we conclude that neural TTS models are overparameterized, and they are highly prunable with simple pruning techniques. We also verify that prune models does produce speech with equal naturalness and intelligibility while preserving the prosody. An even higher level message that we aim to deliver is that pruning could be an alternative tool for us to understand deeper how modern TTS models are trained. And it sometimes reveals properties that were not obvious from before. And this concludes the presentation. I want to thank my co-author who contributes to the project. And if you have any question, feel free to email me. Thank you.